Hello class, in this video I'll be showing you an application of Extrema that requires finding an optimal solution. Let's begin. In this section, you'll be solving optimization problems. An optimization problem requires finding the best possible solution, maximum or minimum, from a list of all possible solutions. The list of all possible solutions must satisfy a certain condition called a constraint. Now I'm going to show you the 8 steps that I'm going to use to solve an optimization problem. Here are the 8 steps that I will be using to solve an optimization problem. I would suggest you become familiar with these 8 steps before continuing on with the video. Now let's take a look at an example. For example 1, we want to find two non-negative numbers, x and y, such that 2x plus y is equal to 228, and x squared times y is a maximum. In part A, we are going to define the variables. The variables are already defined. We have x and y, and they must be non-negative numbers. So I'm going to let x and y be non-negative numbers. Part B, identify the constraint function and solve for one of the variables. The constraint function is going to be 2x plus y is equal to 228. And that is because the values of x and y that maximize x squared times y must be a solution to this equation. Solving for y, we have y is equal to 228 minus 2x. Part C, identify the function that will be optimized. In this problem, we want x squared times y to be a maximum, so that is the function we are going to optimize. I'm going to label the function P for product. Part D, create the objective function and find the domain. To create the objective function, I'm going to substitute 228 minus 2x in for y. That will look like this. And now I'm going to distribute the x squared. So we have p of x is equal to 228x squared minus 2 times x cubed. Now to find the domain. Since x and y are non-negative numbers, then x squared times y must be greater than or equal to 0. Since p of x represents the product, I'm going to set p of x equal to 0. So now we have x squared is equal to 0, or 228 minus 2x must equal 0. Solving the equation on the left, we have x is equal to 0. Solving the equation on the right, we have x is equal to 114. So the domain is the closed interval from 0 to 114. Now to find the critical numbers of the objective function. To find the critical numbers, I'm going to take the derivative of p of x and set it equal to 0. That will look like this. Next, I'm going to factor an x out of each of the terms, and that will look like this. And now I'm going to set each factor equal to 0. We have x is equal to 0, or we have 456 minus 6x is equal to 0. There's nothing to solve for in the equation on the left. We just have x is equal to 0. For the equation on the right, we're going to have x is equal to 76. If x is equal to 0, then x squared times y is equal to 0. So x is equal to 0 will not lead to an optimal solution. So the only critical number we need to consider is x is equal to 76. Part F, verify that the critical number is the location of the optimal solution and identify the optimal solution. To do this, I'm going to apply the second derivative test. So the second derivative of p is 456 minus 12x. If we substitute 76 into the second derivative, you're going to get negative 456, which is less than 0. Since the second derivative at x is equal to 76 is less than 0, then x is equal to 76 is the location of a relative maximum. So now that we know that x squared times y will be maximized when x is equal to 76, let's go ahead and find the value of y. We know that 2x plus y is equal to 228. We substitute 76 in for x and solve for y. We will get y is equal to 76. The maximum product is obtained when x is equal to 76 and y is equal to 76. The maximum product is 76 squared times 76, which is equal to 438,976. And we are done.